So in my last video, I reviewed some basics about being able to evaluate limits that give us indeterminate forms such as 0 over 0 or infinity over infinity. And we stated that if we did it by substitution and got 0 over 0, sometimes we could do something like factor the numerator and denominator and cancel something out and then evaluate it, or multiply by some other fancy form of 1 and then rewrite the expression. But not all forms of expressions can be evaluated that way. Check out e to the x minus 1 over x. Well, e to the x minus 1 is not going to factor into anything good that will cancel, and certainly there's really not much we can do to multiply the numerator denominator by some other clever form of 1 to rewrite this expression and evaluate its limits. So what do? Well, a long time ago, a person by the name of L'Hopital came up with an idea. He said, well, let f and g be functions that are differentiable on an interval that includes c, except possibly at c itself, where we get that indeterminate form, right? If the limit as f of g of x as x approaches c is indeterminate, 0 over 0, then taking the limit as x approaches c of f of x over g of x will be exactly the same as taking the limit as x approaches c of the derivative of f over the derivative of g, provided that that limit on the right exists. All right, so let's see what happens. In this rule, what this is telling us is that if I have e to the x minus 1 over x, to evaluate this limit, rewrite it, so that we would be taking the limit as x approaches 0 of the derivative of the numerator. So let's take the derivative of our numerator e to the x minus 1 and our derivative of the denominator x. All right, so let's see what happens right here. Well, in the numerator, write this out, taking the limit, we're still taking the limit as x approaches 0. Of this new expression, it will be e to the x minus 0 over 1, and letting x approach 0 now gives us e to the 0 over 1. Our limit is 1. Well, that's a nice thing. Apparently, this rule will tell us that if we have a function where it is differentiable in the numerator and denominator, if that limit on the right exists, hey, we're golden. That's actually really, really useful. Well, how did he come to this conclusion? By the way, this result would also apply if we went to infinity over infinity, right, or some form of that. So how did he come to that conclusion? Well, to prove the result, let's kind of remember the mean value theorem. You know, in the mean value theorem, we said that if f and g are continuous functions on an open interval from a to b, on a closed interval from a to b, and differentiable on an open interval from a to b, and there's some value c, where when we take those derivatives, we get f of c over g of c equals 0. Let's see what happens. Well, first of all, right, we would say whatever happens to f prime of x and g prime of x, if we take the limit as x approaches c, we get f prime of c over g prime of c. And by definition, right, one of our alternate forms definition said that the limit as x approaches c of f of x minus f of c over x minus c, that would be the derivative at c. And similarly for g, right? Well, one of the rules tells us that if we're dividing two limits, it's the same as taking a single limit, right? And by the way, if we do that, x minus c cancels out from both of those fractions. We're left with f of x minus f of c over g of x minus g of c. And if we let x approach c, right, we're going to get f of c over g of c. Well, that is the limit as x approaches c of f of x over g of x, right? Because as x is approaching c, what's happening? We're getting f of x minus g of f of x minus f of c over g of x minus g of c. We stated that f of c and g of c is equal to 0, right? And g of c is equal to 0, but that was the limit as x approaches c of f of x over g of x. Therefore, it must be that the limit as x approaches c of f prime of x is the same as the limit as x approaches c of f of x over g of x. See? So that kind of works out.